In 1900, Max Planck introduced a discretization of the energy to derive his successful formula of the blackbody radiation. He intended this only as a math trick, but Einstein promoted it to a true feature of nature. This is the follow-up of the previous video, so in case you haven't, I highly encourage you to watch that first. Last time we ended with Planck finding a physical explanation for the blackbody radiation. The price he had to pay was the introduction of the odd concept of energy quantization. After a couple of years, attempts to eliminate this math trick failed, and in March of 1905, a paper was published that completely opened Pandora's quantum box. His author, an unknown physicist working at the Swiss Patent Office in Bern after failing to find an academic job named Albert Einstein. During his free time, he stayed up to date on new developments in physics and came up with his own ideas. The conclusions of this paper were so outstanding that he received the Nobel Prize in Physics in 1921 for this work. And this was just the first of 4 remarkable articles that he published in 1905. Some of the other papers deserve their own video, so let me know in the comments if you would like me to cover in detail his paper on special relativity. Interestingly, most people think of Einstein as the main opponent to quantum mechanics. We have all read about his disagreements with Bohr and his famous quote, "God does not play dice," as a way to reject the probabilistic nature of the new quantum physics. But I would like to clarify this view here because, as we will see, Einstein was not only one of the early supporters of quantum mechanics, but one of his most influential advocates. Einstein proposed his own quantum hypothesis beyond the reach of Planck's law and showed that it could solve other experimental mysteries of the time. The turn of the century in 1800 came with new discoveries and experimental puzzles. The mystery of the blackbody radiation was finally solved, but others persisted, in particular those related to the nature of X-rays, cathode rays, and the photoelectric effect. At the center of this was an experienced but controversial German experimental physicist called Philipp Lenard. He studied under the guidance of Robert Bunsen in Heidelberg, investigating the conductivity of flames. He is considered one of the key figures on the study of cathode rays and X-rays, which for a long time he thought were the same phenomenon and attempted to prove it experimentally. For years he claimed the credit for the discovery of X-rays. However, only Wilhelm Röntgen received the first ever Nobel Prize for this discovery in 1901, which fueled his bitterness. Lenard introduced important innovations for measuring the properties of cathode rays to try to confirm their electromagnetic nature. But in 1897, J.J. Thompson in the UK demonstrated that these rays are made of negatively charged particles, smaller than atoms. This is considered the discovery of the first subatomic particle, the electron. This discovery completely shattered Lenard's research program of proving that cathode rays were just X-rays, as well as his claims for the credit for the discovery. Fun fact, to this day German-speaking countries refer to X-rays as Röntgen rays. A few years back, a fracture took me to the hospital here in Germany, and I have to admit that seeing a large portrait of Wilhelm Röntgen in the waiting room was delightful, despite the pain that I was experiencing. Lenard moved to his other interest, the photoelectric effect. Heinrich Hertz had accidentally discovered in 1887 that electricity could be produced by shining ultraviolet light on some metals. He was testing the wild prediction of Maxwell's equations that variable magnetic and electric fields could produce electromagnetic waves. In his experiments, the electromagnetic wave was detected as a tiny spark at the ends of a coil. Hertz noticed that the spark was intensified when shining UV light. As a great experimentalist, Lenard spent years investigating the properties of this photoelectric effect, developing new dedicated tubes and methods to measure the energy of the ejected electrons. In 1902, he published his most important work summarizing the results of his exhaustive experiments. One of the most important and counterintuitive observations was that the flow of electrons was independent from the intensity of light. According to Maxwell's electromagnetic theory, when more light was used, the electrons would be ejected with more energy. But Lenard's sensitive experiments showed that by shining more light, the number of electrons increased, but not their energy. He also experimented with different wavelengths and discovered that this was the only important variable. Longer wavelengths, or lower frequencies, produce electrons of lower energy. Light of shorter wavelengths, or higher frequencies, ejected electrons at high energies. All this in contradiction to classical electromagnetic theory. I want to take a minute to thank some viewers for the generous support of the channel on Ko-fi and via Super Thanks. Each video involves long hours of research, scripting, editing, and post-production, so I'm grateful for your appreciation of the content. If you find this and other videos of value, consider supporting the channel. Links in the description below. Another way to contribute is by liking, commenting, sharing, and subscribing. And now we're back to March of 1905, when the physics community was taken by surprise by a paper with the seemingly inoffensive title On a Heuristic Point of View Concerning the Production and Transformation of Light. Einstein opens with a praise for Maxwell's electromagnetic theory. The wave theory of light, which operates with continuous functions, has worked well in the representation of purely optical phenomena and will probably never be replaced by another theory. And then he opens the quantum box. This is how he finished the introduction. It seems to me that phenomena connected with the emission or transformation of light are more readily understood if one assumes that the energy of light is not continuously distributed, but consists of a finite number of energy quanta, which can only be produced and absorbed as complete units. If you watch the video about the blackbody radiation, Einstein's words sound just like repeating Planck's quantization of the energy. But Einstein is not talking about Planck's Hertzian oscillators. Einstein is talking about light. Planck proposed that the charges in a material in thermal equilibrium with electromagnetic radiation have quantized energy. Einstein is promoting the energy quantization to light, and would probably lead many physicists of the time to stop reading. But he continued, "In the following, I wish to present the line of thought and the facts which have led me to this point of view." In what follows, Einstein delivers a masterclass on how theoretical physics is done. To all the people that flood the internet every day with their new theory of the universe or that believe that have overturned a law of physics, take note. Einstein had brilliant and radical ideas, but he presented them step by step, fully motivated, supported by solid mathematical foundations and clear interpretations. He showed how they agree with known physics and make clear predictions to be tested. In one simple calculation, Einstein shows the failure of classical physics. Using Rayleigh-Jeans formula for the blackbody radiation, which follows from the equipartition theorem, he attempts to derive Stefan-Boltzmann law. Integrating the energy density over all frequencies leads to a simple cubic function evaluated at infinity. Notice that Einstein calls the energy density ρ and uses the old notation in which R over n is the Boltzmann constant and L is the speed of light. This infinity is a nonsensical result for a well-established law confirmed by experiments. And I find it quite funny that Einstein doesn't even comment on this preposterous result. For him, it is clear that classical physics just fails. One of the key points in his calculation is the identification of the internal energy of Planck's oscillators with the mean energy of the radiation, which can be calculated using basic probability theory. The probability distribution for a system in equilibrium at temperature T is proportional to the Boltzmann factor, given by the exponential of the energy over kT. And if you remember your probability lectures, the mean energy is given by the first moment of the distribution, where the term here in the denominator is just a normalization for the probabilities to be well defined between 0 and 1. Here I invite you to calculate the integrals. You should get kT squared in the numerator and kT in the denominator, so we find that the mean energy is just kT. This is again the Rayleigh-Jeans relation, which we know leads to an absurd infinite radiation. But let's now follow Einstein's proposal and replace the continuous energy E by the discrete form n times epsilon, where epsilon is a fixed quantum of energy and n is an integer. The integrals over the energy now become simple sums. This expression can be simplified by defining the auxiliary variable r given by the exponential of minus epsilon over kT. What we get is the energy epsilon times the ratio of two geometric series, which we can just check on a table. I forget this all the time, but a quick search shows that the numerator is just r divided by 1 minus r squared, and the denominator is just 1 divided by 1 minus r. Simplifying terms and plugging back the original form of the auxiliary variable, we magically rediscover Planck's mean energy for the blackbody radiation. However, instead of quantized oscillators, now is the light that has a quantized energy. Einstein concludes this section emphasizing that classical physics appears to work at long wavelengths, but at high frequency, these principles fails us completely. The following two sections of the paper contain a remarkable result. Einstein puts Planck's law completely aside and only used the established result valid at high frequencies for the energy density to calculate the entropy of radiation in a blackbody. This is just Wien's law discussed in the previous video. He used two different methods, first using pure thermodynamics and then using Boltzmann statistical mechanics. By forcing the two results to be consistent, he finds that light behaves like quanta with the energy relation proposed by Planck. From this, we further conclude that high-frequency radiation behaves thermodynamically as though it consisted of a number of independent energy quanta of magnitude R beta over n. Beta here is just the exponent in the old notation from Wien, called B in the previous video. And if you read the paper or watch the last video, it is easy to confirm that R beta divided by n is just Planck's constant. So Einstein's light quanta have energy epsilon equals h nu. Again, this feels like redoing Planck's law, but it's different. Einstein's results implies the energy quantization of light, not of the oscillators introduced by Planck. The formulas look very similar, but the conceptual interpretation is radically different. Einstein ends by restating the main idea of his article. The next obvious step is to investigate whether the laws of emission and transformation of light can be interpreted or explained by considering light to consist of such energy quanta. Section 8 of his paper is the finishing blow. Einstein moves to the experimental consequences of his proposal, for which he focuses on the photoelectric effect and the existing difficulties to explain the experimental measurements, emphasizing the importance of Leonard's work. Einstein writes, "If light consists of energy quanta of magnitude h nu, one can conceive of the ejection of electrons by light in the following way." In the next paragraphs, Einstein uses conservation of energy to derive how his light quanta would transfer their energy to the electrons to eject them from the metal, and confirms that his result is in perfect agreement with the observations by Leonard. In modern notation, his formula is written as Kmax equals h nu minus W, where Kmax is the maximum kinetic energy of the ejected electrons, and the so-called work function W is the energy needed to remove electrons from the metal surface, which depends on the material used. This formula shows that the energy of the electrons depends linearly on the light's frequency, where the slope is Planck's constant. Only the intercept depends on the material. If the derived formula is correct, then the maximum energy of the ejected electrons as a function of the frequency of the incident light must be a straight line whose slope is independent of the nature of the emitting substance. Notice that here Einstein makes three clear predictions to be experimentally tested. Prediction number 1 is the linear relation between the electron's energy and the frequency of the incident light. The second prediction is that the slope of the line is independent of the emitting material. And the third prediction is again related to the slope of the line, which corresponds now to a new and independent way to measure Planck's constant. All these predictions can be tested experimentally. Einstein ends with a summary. As far as I can see, there is no contradiction between the quantum of light and the properties of the photoelectric effect observed by Herr Leonard. And then he describes how his proposal agrees with all of Leonard's measurements. What he's basically saying here is, if light really comes in packages of energy h nu, then I can explain all the experimental results of the photoelectric effect reported by Leonard. This article caught the attention of the established physics community, who wanted to know who this mysterious Albert Einstein was. Remember that nobody in the academic circles has ever heard this name before. This is not to say that his proposal was well received. On the contrary, it took many years for Einstein's quantum theory of light to be accepted. Later that year, Philipp Leonard was awarded the Nobel Prize in Physics for his work on cathode rays. In his Nobel lecture, Leonard mentioned his work on the photoelectric effect, but there was no mention of Einstein. although that is not surprising. This part of the story is ugly and sad. You can read the details in the book Serving the Reich by Philip Paul. Einstein's first paper in 1805 describes his idea of particles of light in a way that is so compelling that for a minute the reader forgets that by then the wave nature of light was mathematically and experimentally confirmed. Einstein makes no mention of this great contradiction with Maxwell's theory and the experiments by Thomas Young, Heinrich Hertz, and many others that clearly show that light exhibits wave properties including frequency, polarization, and diffraction. Note that I have avoided the word photon because this name was only introduced in 1924 by the chemist Gilbert Lewis. Einstein's idea of particles of light apparently just ignored a century of experiments, and it took him 4 years to formally address this issue, when in 1909 he wrote, "I was only trying to demonstrate briefly that the two structural properties, wave and quantum structure, should both be associated with radiation." Now, this was not the solution that people were expecting. What he's saying is that when it comes to light, we should consider it as a phenomenon with wave and particle properties. This is the origin of the so-called wave-particle duality of light. I hope that by now you get the picture. Einstein was one of the key players in the development of this theory, and not the quantum physics hater that most popular books and documentaries make us believe. He did have some issues later with the new quantum mechanics, but in the early days he was all for it. Planck was the quantum spark, but it was Einstein who started the fire. Read his papers and you find that Einstein was so pro-quantum that some authors even consider him the true father of quantum physics, because he saw the quantization of energy not as a math trick, but as a true feature of nature, contrary to Planck. The article that I just reviewed in detail in this video is usually called Einstein photoelectric effect paper, but I think that this designation misses the point of the paper. This is not a paper about the photoelectric effect, but rather the introduction of a quantum theory of light, which uses the photoelectric effect as supporting experimental evidence and to make predictions to be tested in the future. His paper on quanta of light was a real bombshell in 1905, and people didn't know that an even more radical paper was coming 3 months later, but that's another story. And yet, Einstein was not done. 2 years later, in 1907, and while most scientists disagree with his quantum theory of light, he decided once again to challenge the status quo by proposing that vibrations of atoms and molecules in solids could also have quantized energy. Einstein was now quantizing particles in solid materials. The key observable in experiments was the heat capacity of solids. This is a property of materials that measures how its internal energy changes with temperature. Using the classical equipartition theorem, the internal energy for each ion in the solid is 3 kT, where the 3 comes from the 3 spatial directions that atoms can vibrate, and K is Boltzmann constant. From here, the heat capacity for a solid containing n atoms is simply 3 Kn. Notice that this does not depend on the temperature. This constant relation, known as the Dulong-Petit law, was proposed by the French physicist Pierre Dulong and Alexis Petit in the early 1800s. This works well at high temperatures, but at room and low temperatures, deviations were observed. The heat capacity appeared to decrease at lower temperatures, but it was unclear if this effect was real and by how much. Einstein decided to propose now a quantum theory of matter by modeling the ions in a solid as tiny oscillators, whose energies can only take integer values of some fixed quantity epsilon equals h nu, where now nu is unrelated to light, but it corresponds to the frequency of vibration of the ions that he imagined as masses at the end of springs. This is what physicists call a collection of independent harmonic oscillators. This was just a toy model. Einstein made some rough approximations like all ions in a crystal vibrating at the same frequency or treating them independently. In a real solid, ions can vibrate at different frequencies and they will form a coupled system of oscillators instead of vibrating independently. But using these approximations, Einstein wanted to know what would happen if the vibrations obey quantum rules. He followed the steps of Planck and determined the entropy of the three-dimensional oscillators, and obviously obtained the internal energy to have the same dependence as Planck's law. Then, taking the derivative with respect to the temperature, he found this relation. As a function of the temperature, this complicated expression looks like this. At high temperatures, Einstein's prediction approaches the classical Dulong-Petit law, but at low temperatures, the predicted heat capacity drops all the way to zero. This was another bold quantum idea, but this was better received because quantum ions were easier to accept than quantum particles of light. Plus, rudimentary cryogenic experiments already showed in 1900 that some light elements like beryllium and carbon deviated from the Dulong-Petit law. Einstein's ideas were radical, and I have not even talked about relativity yet. These ideas were not necessarily liked by the established scientists, but he clearly showed signs of being a great physicist, and his name began to be recognized. His papers were read and cited, and he began to receive invitations to important conferences. During the second half of the first decade of 1900, new techniques, new materials, and electronic devices, in addition to creative experimentalists, allowed the execution of many types of experiments. As Richard Feynman so brilliantly put it, it doesn't make any difference how beautiful your guess is, it doesn't matter how smart you are or what your name is, if it disagrees with the experiment, it's wrong. And it was now time to put Einstein's ideas to test by experiments.